Okay, I want to teach you how to think like a physics expert. And let me start off by saying I don't expect you to be an expert by the end of the video. That's not going to happen. What I want to teach you is how to fake it until you make it. And what you need to understand is I'm not an expert either. My bachelor's is in computer science and my master's is in secondary education. All the physics I've learned has either been from my few high school courses, my few college courses, and having to teach physics. So understand that these are the skills that I've had to pick up, and I think they will help you in the long run. I think what I'm going to show you are skills that can transfer over to any discipline. And we're going to start off with the first one. I'm not sure if it's the most important, but I feel like it's what distinguishes an expert from a novice. And the first one is identifying the concept that's being tested. So if we look up on here, I have my 5 skills that you need to know or be able to do, and I said the first one was identify the concept. I think you may believe that you're already doing this, and that's not true for most of you, because some people may see something and think, okay, this particular question is asking about forces. Great, but there's more to it than that, and especially in school, when you're learning things in units, all your questions are going to be forces questions, or all your questions are going to be energy questions. So that's not specific enough. What I mean by identifying the concept is, as you read through the question, can you identify that it is a second law concept that's being tested? Or as you read through, can you tell from the keywords or the lack of keywords that there's no external work? So then the energy in the system will be conserved. And when you go from reading the question to identifying the concepts, that makes it easier to figure out what you need to do. And I think, especially at the AP level, and that's my dog shaking her collar. So hold on one second. Okay, collar's off. Where was I? So identifying the concept. One tricky thing is understanding that there's a difference between the context that the problem is in the concept that's actually being tested. One of my favorites is imagine you have like a cannon and you're firing a ball out. Well, as that ball's in the air, if we shoot it with like a bullet and that breaks the ball into pieces, given where some pieces land, can you figure out where the last piece will land? And we have to combine multiple concepts here. We have to take what we know about projectiles and combine it with center of mass or momentum. So it's important to identify the context of the problem, in this case projectiles, with identifying the actual concept that's being tested, in this case conservation of momentum or center of mass, whatever you want to call it. Identifying the concept that's being tested is perhaps the one thing that separates a novice learner from somebody who has kind of mastered that content. And it's probably the biggest help, because once you identify the concept that's being used, so if we're sticking with conservation of momentum here, or center of mass, we can kind of know what relationships we need to use. So I think identifying the concept that's being tested is not only what separates a novice from an expert, but also what kind of sets up your ability to solve the rest of the problem. So the next skill we need to work on is drawing our diagrams. I know a lot of students try just to jump into calculations or derivations, but when they ask me for help, I sometimes ask them to draw me a picture of what's going on, or draw me a free body diagram, draw me a energy bar chart. And the reason being is you have to remember, before we started really using words in our different cultures, we always use symbols. And symbols, so that icons, all those things help us take a question and kind of distill it down into what's important. It kind of help us get rid of all the fluff. And I can tell you, if the diagram is specific enough, or if the drawings are thorough enough, I can tell whether or not a student has actually read the question correctly. And I think that can help students figure out what's going on, especially for some questions like momentum problems. Students may draw a diagram for before the collision. And so if we imagine a velocity time graph, momentum time graph, or whatever, their diagram kind of represents a single point in time. But for a momentum problem, we need to be able to handle before and after the collision. So they need to be able to handle the initial velocity and the final velocity. So sometimes we need two diagrams. So that can really help you kind of cut out all the stuff you don't need and focus on what's important. Okay, number 3 is a big one. This is understanding the relationships. Now that we've identified what's being tested, maybe we drew diagrams to figure that out, we need to understand the relationships that are going on. And what I mean by that is, I'm not talking about knowing your different formulas. That's not going to cut it. Because some scenarios will require you to make up your own formula. So it's important that we understand the relationships that are going on. So if I have an object with 4 forces on it, say A, B, C, and D, we need to be able to take our understanding of the concepts that's being tested and relate one thing to another. Because that's what science is. It's investigating relationships. If something happens to quantity A, what happens to quantity B? So in our example here, maybe we're being tested that we know first law in the vertical. So I know the magnitude of A is the same as the magnitude of B here. But maybe it's accelerating to the right, so I need to know second law. Second law tells me mass times acceleration should give me my net force. So it's more than just knowing your equations. In fact, I would rather you use your equations so much that you no longer need to look at them. You don't need to you don't need to look up net force is mass times acceleration. You can focus on setting this equal to the definition of net force. Okay. Granted, we'd add A and add B in there, but they're going to cancel out, so ignore that. And another thing when I'm talking about understanding the relationships, it's more than just using the equation or memorizing the equation. I want you to get to the point where you can look at an equation and say, well, we're only messing with V, so everything else in the equation would be the same. So I really only care about V. So in this case, if I were to double V, it gets squared, so I end up quadrupling the kinetic energy. So double the speed quadruples the kinetic energy, something like that. You need to be able to cut out the stuff that you don't care about. Okay, Another thing I want you to think about is staying calm. When you get stressed, that takes your fight or flight response and kind of activates it. And you have to understand, when you get stressed out like that, your logical reasoning skills are thrown out the window. So I think when it comes to fight or flight, so what separates my best students from the ones that struggle is not like who is smart or who is like a bookworm or who's gifted or talented or whatever. It's the difference seems to be who gives up less often or who takes longer to give up. Basically, my best students choose to stick it out and keep fighting through the problem until they figure out what they didn't know and what they've learned now. So what I want you to do is remember, stay calm. You are learning, and if you don't know it now, we'll work on it and we'll figure it out. We'll know it later, and that's what I want you to do. Keep fighting through those problems, so that way we can learn before the test. That's kind of the whole point, is before stuff starts to matter, can we master this? And that kind of leads me into the next thing I want to talk about, which is owning your mistakes. When you stick it out and fight through a problem and you end up getting it wrong, don't write it off as, oh, I made a dumb mistake, or oh, I didn't know what was going on, and think you're just gonna magically figure it out later. You need to identify the problem, and if you can't, that's why we have the teachers or peers that can say, hey, maybe you're having trouble understanding the question. Maybe it's a reading comprehension thing, or maybe you misapplied a relationship. Perhaps this one tends to come up a lot. Knowing when things are equal, when they're not. Another reason why I hate saying equations, because not all of them are equalities. And when you identify what you don't know or what you can't do, that allows you to improve, because now you know what the problem is. Kind of like the first step to solving a problem is admitting that you have a problem. So the idea here is, once we reflect on what we've done, we can move on. So yeah, I say fake it till you make it, but you also have to think about how you're going to make it. That reflection there is important. So as you learn, as you go through all these problems, all these labs, all these demos, activities, I want you to reflect back and ask yourself why, and that should improve your abilities. So own your mistakes. Be okay with failing. Be okay with making errors. Be okay with goofs, and understand. Hopefully this has been helpful for you. Hopefully this is stuff that you can use in other disciplines, and hopefully that I don't know. Hopefully you learn that you don't have to be an expert right away. This stuff will come with time. So just do your best. That's all I can ask for. And we'll figure this out together. Thank you.